In this video, mostly I'm going to talk about quizzes on the magnetism. Here is the first question. What is the force on a conductor length L carrying current of I when it is placed perpendicular to a magnetic field of 0.2 Tesla? This is F equal to PIL sin theta. Okay, F equal to BIL sin theta, where theta is angle between I and L, or the current flow direction, as well as the theta is between B and I, angle between magnetic field direction and current flow direction. Okay, so he mentioned the conductor is placed perpendicular to the magnetic field, so current is flowing perpendicular to the B, so theta equal to 90 degrees. So F equal to BIL, we know B value, which is 0.2 Tesla, I value 10 ampere, length is 0.2, converted into meters, so 2 times 0.2, which is this is 2 times 0.2, which is 0.4 Newton. So A is the right answer. Next one, next question, which of the following setup has the maximum magnetic field at the center? Goal is finding the maximum magnetic field at the center right here. Now we know from the right hand rule, if the cross indicates that the vector is going into the board, and the dot indicates vector is coming out of the board. Okay, so that's what, so vector is nothing but we indicate with an arrow. When arrow is coming towards us, we see a pointer. When arrow is going away from us, we will see cross at the back. So that's what it is. So according to the right hand rule, the thumb indicates the current direction, the folding fingers indicates the magnetic field direction. So if we look at the first one, so here current is going into the board, so the magnetic field direction here is going to be clockwise. Okay, that's the clockwise direction. So let me take this as 1 2 3 4. So because of 1, the magnetic field direction at this point is, that's magnetic field direction B1. Now because of the conductor 2, current is coming out, it's going to be anti-clockwise. Okay, it's going to be something like this, so that's my B2. Okay, because of 3, that's B3 in the same direction as this. Magnetic field direction is always perpendicular to that circle. Okay, sorry, I did it wrong, so here it is. So it's going to be something like this. B3, the direction is opposite in this direction. Here B4. So because of this setup, magnetic field at this point is going to be 0. Now we'll see the last one. So every current is coming out of the board, so everything is going to be anti-clockwise direction. So it's going to be something like this. Because of this also, here magnetic field is 0. Now we'll see the second set. The magnetic field, because of this, clockwise, so it's going to be B1, again clockwise, that's B2, here it is anti-clockwise, so that's B3, and that's B4. So here we'll end up having some magnetic field going in this direction. So set 2 has maximum magnetic field compared to other 3. Two straight wires run parallel to each other, each carrying current in the same direction. So if current is flowing in the same direction, they experience a force towards each other, but I'll tell you how. So say here is a conductor, current is going in the direction. Okay, so here in this example, current, assume that the conductor 1, conductor 2 both are having the current flow in the same direction. So according to the right hand rule, thumb indicates the current direction, folding fingers indicates the magnetic field direction. So if you look at here, magnetic field is going under, I don't know why it is moving. So here magnetic field is going into the board, here coming out of the board. Now if you look at the second conductor, the second conductor is placed in a magnetic field which is going into the board, and there is a current flowing towards right. If you use the right hand rule, I mean that put your 3 fingers of your right hand perpendicular to each other, thumb, forefinger and middle finger. So middle finger indicates the magnetic field direction, forefinger indicates the current direction, and thumb indicates the force direction. So if you look at here, so we are looking at, because of the current flow in the first conductor, what is the magnetic field direction in the second conductor. So magnetic field is going into the board, so magnetic field, so middle finger, assume that, I mean place that going into the board, and forefinger indicates the current flow direction, thumb indicates the force direction. So based on that, I can clearly see this conductor is moving up. Okay, now if we look at the second conductor, because of the current flow in the second conductor, the magnetic field here is coming out of the board, here going into the board. Okay, so if you look at here, the magnetic field is coming out of the board. So the first conductor is placed where magnetic field is coming out of the board and the current is going towards right. So basically that's going to move towards down because the magnetic field direction is changed. So if current is flowing in the same direction, they attract each other in the same direction. The force between them is attraction force. Here is V indicates the velocity of a positive charge and the direction and its direction, and B indicates the magnetic field and its direction. In the following figure, find the direction of the force. So here also we are using the right hand rule. Always thumb indicates the force. Okay, middle finger indicates the B, and the forefinger indicates the velocity V. Okay, here the next question, thumb indicates the force, it's not going to change. Middle finger indicates B, and forefinger indicates the current direction. Okay, so in the first case, place all 3 of them perpendicular to each other. So now middle finger indicates the B, so middle finger indicates the B, and forefinger indicates the velocity. Velocity is going into the board, right? So the cross indicates that is going into the board. So when you place your right hand in that direction, indicating middle finger indicating the magnetic field direction, and forefinger indicating the velocity direction, then I see the force is towards down. Okay, force is towards down. Now the next one, the current and B. So B is coming towards down and current is coming out of the board. Okay, so if you place all 3 fingers in the direction, I see that the force acting on that conductor is going to be towards right. Okay. Next video, the direction that an induced current flows in a circuit given by the direction of the current, we always by using the Lenz's law. Okay, the next one, currents circulates in a piece of metal that is pulled through a magnetic field, what are those currents called? Those currents called eddy currents. Okay, that currents are happening in the iron core, so also called core losses. Okay, the induced EMF around the given loop, if the rate of change of magnetic flux is 50 Tesla per second. So induced EMF E equal to N times d phi by dt. Okay, N is number of turns. We have only one turn. Phi is nothing but BA cos theta. Theta is here is 0 degrees. Okay, so why it is 0? Theta is angle between normal to the area. So normal to the area is perpendicular to this area, which is also either going into the board or coming out of the board. And magnetic field here, they are dots, so they're all coming out of the board. So phi, I can write it as BA, so dB by dt times area. Area is constant, but the magnetic field is changing at 50 Tesla per second. So we know that area is 4 centimeter square. So 4 times 10 to the power of minus 4 times 50. So 200 times 10 to the power of minus 4, 0.02 volt. Next one, a coil with area of 2 meter square rotates in a 0.01 Tesla magnetic field at a frequency of 60 Hz. How many turns are needed to generate a peak voltage of 160 volt? Okay, for that we already have a formula here. Emax equal to omega times ABN. So the peak voltage is given 160 volt. Omega is 2 pi f, 2 pi times 60, and area is given, a coil with the area of 2 meter square, and B is given, which is 0.01. Okay, and we don't know N value. What is the N value? Use the calculator. 21 turns. Okay, the next one, what current is changing? Which current is changing more rapidly? So here, induced EMF across the inductor is L times di by dt. That's the induced EMF across the inductor. So L value here is 1. So this value is 1 of 4 volts. So L value is 1. So di by dt equal to 4 in this case. Here 2 times di by dt equal to 2 volt. So what is the rate of change of current? Is 1 ampere per second. Here 4 ampere per second. So basically I can see I2 is changing more rapidly than I1. Okay, let me go with the next quiz. Here is the next quiz. The inductor is initially uncharged and switch is closed at t equal to 0. What is the current supplied by the source immediately after switch is closed? So immediately at t equal to 0, inductor is going to behave like a open at t equal to 0. Once it is fully charged, it will act, after some time it will act like a closed circuit. That some time is, we're talking about probably microseconds. So at t equal to 0, that's going to act like open circuit. So I equal to V over, since once we close the switch, current is going to pass through only that R. So I equal to V over R. That's a transformer is, it boosts the maximum current provided by the battery. No. It changes mechanical energy into electrical energy. No. Changes the voltage level of an AC voltage. That looks good. Converts alternating current into direct current. That's wrong answer. Transformer either steps up or steps down the voltage at the same time. It steps up or steps down the current. So whenever it is stepping up the voltage, it is stepping down the current, and vice versa. So C is the right answer. Now next one, if the top circuit has an oscillation frequency of 1000 Hz, the frequency of the bottom circuit is, so the frequency, oscillations of frequency is basically f equal to 1 over 2 pi square root of LC. That value is given as 1000 hertz. Okay, here these two capacitors are in series. When they're in series, the total capacitance is C by 2. Okay, so F equal to, in the second circuit, let me take that as F1, F2 equal to 1 over 2 pi square root of L times C by 2. Okay, so C by 2 is nothing but 1 over 2 pi square root of LC, and square root of 2, I'm going to put the square root of 2 up there. So square root of 2 times, so F2 equal to square root of 2 times F1, which is 1410 hertz. The magnetic field strength current carrying wire is parallel to the wire, inside the wire, perpendicular to the wire, around the wire. We know that magnetic field strength is always around the current carrying conductor. Compared to the magnetic field at point A, the magnetic field at point B is, so the formula for magnetic field, B equal to mu naught I over 2 pi R. Okay, so BA, say magnetic field at BA is, say I'm going to take that as 10 Tesla. So BB, magnetic field at B, is going to be, can I say this is only 2 centimeters, that is 4 centimeters. So BB must be, can I say it's going to be 10 divided by, that's a 4 centimeter, that 10 divided by 2, because length is doubled, so it's 5. So compared to the magnetic field at point A, the magnetic field at point B is half of the point A. I'll stop this video here. I'll continue on in another video.